Okay, if I've got this is my 2-methyl heptane. If I make the next isomer, I'm going to do the same thing I did before. I'm going to pull this hydrogen out. I'm going to grab a methyl group off this end, stick it on there. Notice how much activity I have going on this end carbon. How much more condensed this molecule is. Now, a real molecule wouldn't have these sticks in it. These balls would just be clumped together. And it would actually be even busier at this point. It would be really hard for this to react. So if I think about it that way, when this combustion reaction occurs, I need these oxygen molecules to slam into this hydrocarbon. And so it's easy for this single oxygen to hit any one of these on the carbon chain, but once I start getting these CH3 molecules condensing around each other, it gets harder for the water molecule to hit any specific one of them. In fact, they're really guarding this central carbon. If I make that last constitutional isomer, I'm going to see that same phenomenon occurring. Come on. When I put this whole thing back together, this is 2,2,2,2,3,3 tetramethylbutane. When I put this whole thing together, it's really busy. It's really got a lot going on. It's got a lot of all of these carbon atoms are really condensed around the same point, which makes this more difficult for anything to interact with it, for anything to react with it. And so when I have this in reactions, this can hinder a reaction from being able to occur. We'll see this a lot when we start to look at substitution reactions and elimination reactions. And this has a particular name. This is called steric hindrance. It's hindering a reaction from being able to occur, hindering a reactant from being able to get in and react with one of these carbons. I don't know where the word steric comes from, but this is the name we have for this type of phenomenon. This is going to come up again a lot when we look at reactions. So steric hindrance, this is a concept you should become more familiar with. The last section of this assignment is going to have us look at cycloalkanes. Now we're going to do a lot of what we've already done. We've got our compounds. I just drew it out instead of writing it out. We've got our enthalpies of combustion. But what's different about cycloalkanes is that each carbon is just going to be bonded to 2 hydrogens. So every carbon on this is going to be a CH2. And so I can just count the number of carbons to find out the number of CH2s. So in cyclopropane, the number of CH2s, 3. Each one is a CH2. For cyclobutane, it's 4. So on and so forth. I think you can figure that out. So I want you to make the formula here. This generalized formula is just going to be CnH2n. All right? And then I want you to figure out the kilojoules per CH2 molecule. See if we can find a similar pattern as before. Remember, the lower that number here, the more stable that molecule. In other words, the higher that number, the easier it is for that molecule to break apart. So we're going to examine that. We're going to be looking at that. And what you're going to do first is once you've got those numbers, you're going to go in and you're going to graph these results. So I want you to graph the compound, the number of carbons, versus the enthalpy of combustion. Not the difference, not the average, but the actual enthalpy of combustion. I want you to see if you can find a pattern in the graph, just like you find a pattern in the data.